Hello everyone, this is Casey with Foundation Testing and Consulting. In this video, I want to provide an overview of what evaluation criteria should be used for the analysis of CSL test results, that is for cross-hole sonic logging of drilled shafts. Spoiler alert, I'm in favor of using the original Federal Highway Administration Condition Rating Criteria and not the guidelines published by the Deep Foundation Institute, DFI, in 2019. Let's start with looking at an example of data analysis for assessing a drill shaft anomaly from CSL test results. As we can see, this is the apparent sonic velocity, which is computed by taking the distance between the CSL tubes and dividing it by the first arrival time. And here's a plot of the signal energy. And we're collecting data every 2 inches along the length of the shaft. And this is the stacked arrival time plot, often called the waterfall plot. And you can see we've got a departure here at the base of the shaft where our apparent sonic velocity decreases, our energy decreases, and we have significant feigning or loss of signal at the base of the shaft. So it's clearly a common bottom shaft anomaly. We've seen it many times. It's indicative of concrete and water mixing during placement. So we're going to go through here. This is how, in brief, how you would do the analysis. So you pick a spot before there's a departure in the velocity at a discrete zone. So in this case, our typical sonic velocity is around 13,000 feet per second. So we're going to look at where that velocity decreases by more than 10% and then note it in our report. So if you go down here, and about here is where we start dropping down below 11,000 feet per second. Even lower, getting close to the velocity in water, the compression wave velocity in water. So clearly this is a bottom anomaly. Normally I just look at energy in a qualitative fashion. Yes, we see that the energy decreases where the first arrival time increases and the computed apparent sonic velocity decreases. So that's it in a nutshell. That's how you do this type of analysis. And of course, you need to ferret out an issue with the drill shaft concrete itself versus things that are merely a data issue from, say, access tube debonding. So for this example, we obviously have questionable to poor quality concrete in about the bottom 2 feet of the shaft. And I say questionable to poor quality concrete, we see velocity reductions of 10 to over 50%. Now there's a Federal Highways Administration publication that covers drill shaft design and construction. I'll put a link to this document in the description for this video. This FHWA manual is titled Drill Shafts, Construction Procedures and Design Methods that was published in September 2018. In this manual, the standard evaluation criteria for drill shaft anomalies is presented, which in its basic form has been used successfully for well over 20 years in the United States. This criteria is based on an assessment of ranges of reduction in apparent sonic velocity, which should be used in conjunction with reduction in signal energy, just as we saw in that previous example. Now, the reduction in apparent sonic velocity should be computed for discrete zones in the shaft. Keep in mind that I say apparent sonic velocity because this value is computed as the horizontal spacing between CSL access tubes, which is assumed to remain constant along the length of the shaft for a given combination divided by the first arrival time. Now, we can have variations in the tube spacing along the length of the shaft, and it's readily apparent. It's of no consequence. It's not going to affect our calculation since we're looking at discrete zones of an abrupt decrease in apparent sonic velocity along with a decrease in the signal strength. So the first arrival time is the time it takes for the CSL pulse to go from the transmitter probe in one tube to the receiver probe in another. Now you can see that there are various ranges in concrete condition rating from good quality concrete to questionable quality, poor quality, to no signal. There's also a special case worth noting where the apparent sonic velocity is around 5,000 feet per second, which is the compression wave speed in water. Such a result would typically indicate complete washout of cement paste and fine aggregate, which leaves a water-filled zone of coarse aggregate, typically at the base of the shaft, but it could also occur in other zones of the shaft, particularly if there's an issue with the tremie being pulled out too far or plugging, and they remove it and reinsert it, which is not a good idea. Now I noticed that the 2018 update to the FHWA Drill Shaft Manual changed the condition rating criteria to also include ranges in reduction of signal energy. The older condition rating criteria does not factor energy into the assessment except in a qualitative manner. In my opinion, I recommend using the older condition rating criteria. The reason for this is that an anomaly that is truly the result of reduction in concrete quality in the drilled shaft will have a reduction in apparent sonic velocity, which is a direct result in an increase in the first arrival time. But such zones will also have a corresponding reduction in signal strength. In my opinion, there is absolutely no reason to calculate the percentage reduction in signal energy, as I think that is totally unnecessary given the inherent reduction in apparent sonic velocity for the anomaly. Attempting to calculate energy reduction levels simply adds unnecessary time to what it takes to complete the analysis of the test results and issue the report, in my opinion. I also think that such an approach that the DFI is promoting creates a sense of false accuracy. As I've mentioned in previous videos, I have performed CSL data collection and analysis for over 15,000 drilled shafts during the last 22 years. The vast majority of those test reports were issued using the original drill shaft condition rating criteria, and I've been quite successful in accurately identifying and delineating where reductions in concrete quality have occurred within drilled shafts. I know this because in many cases the shafts had subsequent coring, or we did tomography, and the results corroborated our original findings. Unfortunately, DFI is promoting their own guidelines for evaluation of CSL test results that place even more undue emphasis on delineation of the magnitude of signal energy reduction, in my opinion. I came across the DFI white paper, these guidelines, a few years ago when an engineer had the opportunity to require its inclusion in the drill shaft specification for a project that I was involved in. Apparently, DFI decided to form a committee to solve a problem that I don't agree exists in the way that they stated. And here I quote from their guidelines. Over time, CSL rating criteria based on first arrival time and relative energy have incorrectly evolved to often be the sole means of determining the acceptability of a shaft. Some of these criteria have found their way into regulatory agency specifications, with acceptance values often differing from agency to agency. So let's unpack this quote. In my opinion, no single test method for assessing the integrity of the concrete in a drilled shaft should ever be used as the sole basis for shaft acceptance. As such, there is no issue with the conventional CSL rating criteria, in my opinion, that accounts for localized decreases in apparent sonic velocity and only considers associated reductions in signal energy in a qualitative fashion. In my opinion, DFI instead should have focused on a more comprehensive approach for determining the basis for shaft acceptance or other action following the CSL testing by doing such things as reviewing shaft design requirements and installation records and observations that were made during the time of placement. DFI also could have provided more details for follow-on investigation methods such as CSL tomography, concrete coring, CSL testing between the core hole and the CSL pipes, and other methods. I provide an overview of these methods in this video. It should also be noted that the Federal Highways Administration Manual considers the DFI guidance to be preliminary and should not be used as a replacement to the conventional concrete condition rating criteria. The end result of the evaluation criteria by DFI end up in a table like this. You can see per this table you have a concern about drill shaft concrete quality based solely on a reduction in signal energy, which simply does not make sense. In fact, nowhere in the DFI guidance is there any differentiation between a true drill shaft concrete quality issue and mere data issues that are in no way related to variations in concrete quality. An example of this would be where you have CSL access tube debonding at the top of the shaft. So you can see here that we've got, from the waterfall plot, we have some signal feigning, but you can tell that these parallel lines in the waterfall plot are in fact parallel even through the zone of attenuated signal. So this is a classic indication of access tube debonding. The debonding gets bad enough at the top that we actually don't get a signal in the top 6 inches of the shaft. But again, this is classic access tube debonding, and what we find is that some combinations will show this and others won't, and usually the combinations that do are common to a specific access tube or tubes. So it's readily apparent that this is access tube debonding. In such debonded zones, it's possible to have enough attenuation such that the apparent first arrival time is delayed. In such cases, it's the role of the testing consultant to call out such zones of debonding and not merely lump them into a concern about drilled shaft concrete quality by robotically calculating apparent signal loss and increased arrival time in such zones. Earlier I mentioned a project where I was performing the CSL testing and the project specifications had been modified to require the DFI evaluation criteria instead of the state standard criteria for CSL evaluation, which followed the original FHWA guidance. On that project, there was clear instances of access tube debonding that had nothing to do with any variation in concrete quality. Yet the engineer reviewing the reports for the owner insisted that I robotically calculate the signal reduction and increase in first arrival times in such zones in an effort to adhere to the DFI evaluation guidelines. All this did was to unnecessarily delay the contractor in completing their work associated with follow-on construction, in my opinion. What's ironic to me is that there are many engineers in the industry promoting this DFI evaluation criteria for CSL test results who are also promoting use of thermal integrity profiling as a primary drill shaft test method. Note that for thermal integrity profiling, there are currently no industry accepted standards for how such results are to be evaluated. And again, if you look at one of my previous videos, I recommend that CSL be the primary integrity test method for a drill shaft. And to the extent that thermal integrity profiling is done, it's only done as a supplement and certainly never as the primary test method for a drill shaft. I will be posting videos in the future that detail my experience and recommendations regarding thermal integrity profile tests for drill shafts, so be on the lookout for that. For now, let it suffice to say that I have advised several contractors who are responsible for installing drill shafts where thermal integrity profiling will be performed that they are in essence writing a blank check. That is, why would anyone want to be responsible for the drill shaft placement where the owner may require additional tests or even reject a shaft based on the results of the thermal integrity profiling results, where there are absolutely no evaluation criteria listed in the project specifications? Again, that's a topic for a future video. So my recommendation is that DFI evaluation criteria not be used at all in favor of using the original FHWA evaluation criteria for CSL testing of a drill shaft. If you enjoy or can benefit from this type of content, please hit those like, subscribe, and notification buttons, and please stay tuned for future videos. Thanks very much.